Hello everybody and welcome to the final presentation of the Group 6 for the OGO Energy Challenge. My name is Angin Mišić and I'm the communication manager of the group, and together with my colleagues Bart, Pim, Niki and Yavi, we are going to present what we have done so far in the previous 6 weeks and what are our plans for the following time that comes. First of all, I would like to introduce the main goal of this project. We were hired by the company named TUE Vehicles to establish and manifest the most energy efficient driving strategy for going around the track. The car we got is a scaled down version of the Audi A4. It has electric motor and it's remote controlled. On this car, we have done various experiments and tests in order to conclude what setup of the car should be used for the most energy efficient drive. We've done that by separating our work equally among the group. We had 2 or 3 persons working on every experiment in order to do things most time efficiently. We have those people working on the experiments and reporting afterwards about them. All that about the experiments you're going to hear from my colleague Niki.
So for the tank to wheel analysis, we have done 3 experiments. One is for the rolling resistance. It was a coast down experiment at the mate forum. The other one is an aerodynamic drag test, which was done by placing the car inside of a wind tunnel, which OG will tell more about. And then the internal losses, which are the losses within the vehicle itself. So the losses of the battery, the idle consumption, and the losses of the motor and the drivetrain, which Pim will tell more about. I will tell more about the rolling resistance. For the rolling resistance test, we have done 2 different tests, one with the coccycle connected and one with the coccycle disconnected. We did one with the coccycle connected to obtain the total resistance force on the car, and we did the second test to just calculate the resistance force on the car from the tires. So that's only the rolling resistance of the tires. For every test we used 2 different heights. We used these 2 different heights to obtain different velocities to look if there's a difference in the rolling resistance coefficient at those velocities. We've done 3 runs for every height, so we could average them out and get an even preciser number for the rolling resistance. Here you can see our graphs on the rolling resistance coefficient. When the coccycle is on, there were more fluctuations. This is because of the internal resistances of the car. And when the coccycle is disconnected, it reaches higher velocities because the rolling resistance was lower, so it could obtain higher velocities. As you can see, the rolling resistance coefficient is almost constant at low velocities. This is just as we expected, because there isn't a big influence on the tires. Now OG will explain more about the wind tunnel test.
The aerodynamics, or the wind tunnel test, has been conducted in 3 major steps. The first step we needed to do before getting to the tunnel itself was measuring the frontal area of the car. That was done by using the Clunk. Clunk is the area measurement software which we found online. Basically what we did is that we took the picture of the car. We used Clunk to outline all the edges of the car itself in the picture. Manually we measured with a ruler the distance between 2 wheels, and we used that distance in the software as a constant to measure the whole body of the car, the whole frontal area. After we've done that, after we had precise measurements, we could proceed to the wind tunnel. We placed the car in the wind tunnel itself, which is done by this. The wind tunnel consists of the platform, wooden platform, which hangs from 4 different wires, thin wires, around 5 millimeters above the surface, and it's connected to the force sensor. So wind blows in the direction to the car, it pushes the car backwards, and the force is produced and measured on the force sensor. We've done that in 5 different setups. We used 5 different versions, adding wheel covers, front splitter, and rear spoiler. And the measurements we got for the force, we put in the equation we found also online. The equation consists of the force we got, air density, drag coefficient, frontal area, and the speed of the wind. From this force, we derive the equation for the air drag coefficient itself, and by using that final formula we could derive this from the all 5 setups. The setup that got the least amount of energy coefficient drag coefficient was front splitter and wheel covers only on the car. That was displayed here in the graph. And also one interesting thing that happened was when we added rear spoiler, we got enormous increase in the air drag coefficient, but also we got the increase in the downforce in the car, which, for example, in Formula 1 is used to push the car backwards a bit, so it increases the grip. But when we talked to the group, we decided to use front splitter and wheel covers only in order to get least energy losses. Next is going to be Pim to tell you a bit more about dynamo.
So hello. For the dynamo lab test we did 3 different tests. The first test was with the motor disconnected from the battery, and the dynamo was turning the wheels. So all the power was coming from the dynamo itself. This test was to calculate the rolling resistance losses and the internal losses in the car. We aren't able to calculate these losses separately, but we still need these losses for our final calculations in the end, and for the efficiency calculations. I will show you that later on. For the second test, the battery was actually connected to the motor, and we made the car drove under different road load parameters that we already set up in advance for different velocities from 0 to 45 kilometers an hour. For the third test we measured the idling consumption. Here the battery was also connected to the car, but the car was standing still doing nothing. This was to measure the auxiliary losses, the idle consumption, which goes to, for example, powering the ESC or powering the radio transmitter, and this is basically power you always need, so you always need to take this into consideration when you're doing calculations. So these are the results of the first tests, and the power that is displayed here on the y-axis is actually power losses in the drivetrain and due to rolling resistance. We weren't even able to calculate this rolling resistance power, as I said, because we don't know the rolling resistance coefficient between the iron of the dynamo and the rubber of the wheels. You can see that there's an almost linear increase when the speed increases, the almost linear increase of power loss. So these are the results of the second test. You can see that we've done these tests for values from 5, 10, 20 and 30 newtons of load force, ranging from 0 to 45 kilometers an hour. The power that is shown on the y-axis we calculated that by multiplying the battery output voltage times the battery output amperage, the current I mean. Oh, I'm sorry. As you can see, these graphs, it's hard to see in this picture, but these graphs don't start at 0, and that's because we have an idling consumption that's always being consumed, even when the velocity is 0 kilometers an hour. So with all these tests that we did and all the values that we got, we were able to measure the efficiency of the engine. We used this formula for that, where P dynamo 2 is the power at the wheels in the second test, so the power measured at the dynamo during the second test. P dynamo 1 is the power delivered by the dynamo in the first test, so these are the power losses in the car, and for the rolling resistance on the dynamo. The P battery 2 is the power taken from the battery during the second test, and P auxiliaries is the idling consumption, the auxiliary losses. We calculated this and we formed an efficiency map, and as you can see on this efficiency map, the car is most efficient between 20 and 25 kilometers an hour. So we can conclude from test 1 that when you drive at a higher velocity, there is more rolling resistance and internal drivetrain losses, and like I said, we can split these up, but we still needed this for our calculations. In the second test, we can see that there's a linear increase when the road loads are lower, but when you increase the road load, there actually starts to become an exponential increase. This means that when you drive a higher velocity, there's decreasingly more power needed. For the third test, we can conclude that there's an idling consumption of 2.2 watts. So this means that there's always 2.2 watts consumed, even when the car isn't doing anything. The final conclusion we can take is that when the road load force gets higher, you should drive a higher velocity to stay efficient. And now Bart will tell you something about the driving strategy we came up with.
Well, so the driving strategy consists of driving in a straight line, optimal efficient velocity, stopping, acceleration and cornering, where Javier will tell something about, and I will do the optimal driving speed. So, from the previous tests we got the road load function, so you can input a velocity and it outputs the road load connected to that velocity. So we turn that around and now you can input the road load and we give it the speed and at that speed you will have that amount of road load you inputted. So from the dynamo test we got 4 tables, one of 5 Newton, 10 Newton, 20 Newton and 30 Newton. So there was a constant amount of road load and they varied the speed and the given battery power connected to that speeds. So if you input 5 Newton into this formula, it will output a velocity of 80 kilometers an hour. And well, if you make using polyfit of MATLAB, we created an equation of this table. So in that table you could input a velocity, and we inputted 80 kilometers an hour, and it will output the battery power which fit to that velocity. So we did that for the 10, 20 and 30 Newton as well. So you get this graph. So at every speed you can get the battery power. Then we convert that into this graph. Again, for every speed it outputs the amount of joule per meter the motor used. So you can see that the optimal velocity is at around 22 kilometers an hour. So now will Javier continue?
Thank you, Bart. So moving on to the next part of the driving strategy, it's the acceleration itself. So the driver can accelerate in 2 different ways. One of them is using a maximum acceleration to get to the desired speed as quickly as possible, or a steadier acceleration which takes more time to get to the desired speed. So the optimal to desired speed. Okay. So the optimal acceleration is based on the assumption that when the driver is accelerating, the car is in an inefficient speed regimen until the most efficient speed is reached. Since the most efficient speed is 6 meters per second and the time taken to get to the optimal speed is very short, the difference between the acceleration strategy wouldn't be that big. Although we decided it would be better if the driver accelerates as quickly as possible to the 6 meters per second, the desired optimal speed, to stay in the efficient regimen for as long as possible. Although it is important to be able to calculate the amount of energy used to accelerate to the desired velocity, so this can be done using the equation of kinetic energy shown on the slide here. So from a standstill, the energy can be calculated from this to the 6 meters per second, which is the optimal speed, which would total in 215.1 joules to reach the optimal speed. Moving on to braking, which is the next large component in the driving strategy, braking itself is when a car brakes, the kinetic energy is converted into heat by the brakes due to friction. This energy cannot be recovered and will be completely lost. So this energy loss can be calculated using the equation shown on the slide here.
where this is the energy loss, this is the mass of the car. V1 is the initial velocity before braking, and V2 is the velocity right after braking. And below is another equation where E braking is the energy converted to heat during braking, and E other is the energy loss due to the aerodynamic drag, the internal drivetrain, and the rolling resistance. So as braking from a mobility standpoint is a pure loss of energy, so it should be avoided as much as possible if you want to have an efficient driving strategy. So for this reason, it is recommended for the driver to let the car coast. So coasting is simply done by letting go of the throttle until the car comes to a complete standstill or reaches a low enough velocity for cornering. So braking should only be used if the driver is too late with coasting, or doing unforeseen situations, or if the car is going too fast before the point where it's meant to start coasting. So to make a proper use of coasting strategy, the distance covered while coasting from the optimal speed to a standstill needs to be determined. This was calculated by using the following equations, where V is the optimal speed. So the power loss, the P loss, is the sum of the total forces, resistance forces, multiplied by the velocity. When I mean resistant forces, I mean the rolling resistance, the air drag, and the internal resistance. Once the integral over time of the power loss is equal to 215 joules, which is the kinetic energy at the optimal speed, the car would have come to a full stop. Since rolling resistance and aerodynamic drag are defined functions from the experiments that were carried out before, it is possible to calculate the power loss precisely. The energy losses are then assessed for intervals of 0.1 seconds until the energy loss equals the kinetic energy. Next, all the distances from these intervals are added up together, and this gives us our total coasting distance to come to a full stop, which is 22 meters. So moving on to the final aspect of the driving strategy is cornering itself. So there are several ways a driver can take a corner. So one of them is by taking the shortest corner. This is where you just simply follow along the inside of the corner itself. Although to be able to do this, the maximum cornering velocity has to be larger than the optimal velocity itself, or else it would you would have an oversteer or understeer depending on the corner. Another option is to take the fastest corner, but this requires a very strong brake just before the corner and a very strong acceleration right after. This would be great for racing, but not for efficiency. On the slide right here, you can see what is considered to be the most efficient strategy for taking a corner. And this is by using the apex. The apex of a corner is usually the geometric center of the corner itself. In this way, the radius of the corner is at maximum, and the radial acceleration is minimum, and therefore you have the highest cornering speeds. Therefore, the car has to brake less before, and it has to accelerate after the corner, and you remain at an optimum speed for longer. The bigger the radius of the corner, of course, the smaller the radial acceleration. This means that less grip is required, and hence less rolling resistance is applied on the car. The maximum speed for cornering can be determined from these equations on the next slide. Went too far. Which can be seen on this slide right here. So yeah, these are the equations we use to calculate the maximum cornering speed, which for the track itself, there are different corners which we had to take into account for each one, and trying to have the shortest track possible, as well as using the optimum corner strategy, we came up with this plan for the track itself to be used on the challenge day, for which we would start at this point here, circle around. As you can see here, we try and follow straight around the corner as small as possible, as tight as possible. At this point here at the blue dot is where the driver should start coasting to be able to come to a full stop at the stop mark. This distance marked in this red line at this point is less than the 22 meters, as there are two corners in between, and that would it would cause a loss in directional velocity. So it would be less than 22 meters, as you would have lost some of the velocity due to coasting when you're cornering. Moving on, so that was it for the driving strategy. I will now pass it back to Bart for him to talk about the Arduino and the velocity measurement system.
Right. So now we know the optimal driving speed. We need to show that to the driver while he's driving around the track. Therefore, we use an Arduino. That's much used by beginners of programming because it's very easy to learn. So because of that, we were able to do it. It consists of a microcontroller that was programmable by Arduino programming language. It has an input and output. So if you have a sensor, the whole sensor in our case, it inputs a signal, and Arduino can do some calculation with that, or output the signal to, for example, a motor or other stuff. You can also use serial, so you can input a signal to the Arduino using your keyboard, and just write a number or text. And it can also be used as output, so you can read what Arduino is doing on your laptop. And in our case, in this project, we use the Arduino GUI. You can see it right here. It's very useful for this project because it's large. It has a lot of pins, so you can attach a lot of sensors and LEDs, for example. Now we need to calculate the RPM of the drive shaft of the car. So we use the Hall sensor. If a magnet passes the Hall sensor, it will create a pulse, a signal to the Arduino. So one cogwheel on a car, we implemented 2 magnets. So every rotation of that cogwheel, Arduino will get 2 pulses. Now you can do writing code to calculate the RPM of that cogwheel drive shaft. We have got 2 ways for that. The first one is to measure the amount of pulses during for example, 1 second as a certain amount of time. We used the way to measure the time between 2 pulses. So now we know the RPM of the cogwheel drive shaft, but we need to know the RPM of the rear wheel drive shaft. So we use the gear ratio between the 2 shafts, and then you can calculate the RPM of the rear axle. So then we use the circumference of the rear wheels and use the formula diameter times pi to calculate the amount of distance the rear wheel will travel during 1 rotation, and then using that you can calculate the velocity of the car. Now Nicky will continue.
The Arduino LEDs. On the Arduino are 4 LED bars, one on the front, one in the back, and on both of the sides there's one. Each LED bar consists of 33 LEDs. Every LED consists of 3 diodes for the colors RGB, red, green and blue. Every LED bar is represented in the Arduino language with an array of 96 bits. So for every diode there is 1 bit. Every bit is either 1 high voltage or 0, which is low voltage. At high voltage the diode is on, so it gives its color, and at 0 it's low voltage, so the diode is off and it gives no color. To put bits into the array of the LED bar, we have the clock cycle, which starts with the SDI. The SDI is either a high or a low voltage, which is 1 or 0. And then the clock goes to high voltage, and the bit is shifted into the left side of the array. Then the SDI changes from voltage, so either low to high or high to low. Then the latch goes to high, and when the latch goes to high, the shifted array is implemented into the LED bar, and the diodes change from color, or change from high to low or low to high. Then the clock and the latch both go to low voltage, and one clock cycle has been done. So there's actually the array shifted, one to the left, and there's one bit added. To change all of the diodes, you have to repeat this 96 times to actually have a full new array to be able to color code the LED bars. We've color coded the LED bars in the next order. When you're driving too slow, the bars are just empty. When you're going to the right speed, the bars fill with the color green. So when they're half full, you're halfway to the optimal speed, and when they're full, totally full, you are at the right speed. When you're totally full, it becomes blue. The color green turns into blue. And when you're going too fast, it will slowly turn red. So that the driver knows that he either has to brake or just release throttle and let the car coast. That's it for the Arduino LEDs, and OG will conclude this presentation.
Thank you. With this slide, we would like to conclude our presentation, but before that, we would like to we hope that you understand what was going on over the past 6 weeks, and in front of us there is still a challenge day and also a final presentation where we have to write everything we have done so far in detail and to elaborate our results. Hope you enjoyed and understood everything we said, and thank you for watching. Goodbye.